Hi everyone, let's continue with confidence intervals. Before, in lesson 28, we used the z-distribution to estimate a population mean mu in the case that sigma was presumed known, although this was the rare case. If anything, lesson 28 was more useful in preparing us for lesson 29, where we used t-distributions in the case where sigma was presumed unknown. So you might be wondering, well, what's the point of using the z-distribution when doing confidence intervals? Actually, the z-distribution, the standard normal distribution, may be more useful in lesson 30, where we're going to do point estimates and, more importantly here, confidence interval estimates for p, which is a population, proportion, or probability. We're going to use the standard normal z-distribution to develop confidence intervals, 1 minus alpha confidence intervals, CIs, for p, a population, proportion, or probability. So this is a great lesson for politicians who care about polls and proportions of voters, and what politician doesn't care about that? Or maybe you have friends who are gamblers or magicians and they care about probabilities. Either way, this lesson can be very handy. Again, in this lesson, we will find 1 minus alpha confidence intervals. The most common confidence level is 95%, or 0.95. Although there are others. For example, some other popular ones are 90%, or 0.90, and 99%, or 0.99. I can ask you about a variety of different confidence levels. But the gold standard is 95%, or 0.95. In fact, when you hear about polls in news reports or from the news media, the normally assumed confidence level is 95%, or 0.95. And statisticians are really irritated by the fact that news organizations don't report that fact, that the assumed confidence level is 95%. News organizations tend to report the margin of error, E, for their polls, but they usually don't report the fact that the confidence level is assumed to be 95%, or 0.95. Statisticians think that that should be reported. In lesson 30, we're going to find 1 minus alpha confidence intervals, CIs, for P, a population proportion, like if you're a politician who cares about polls, and they all do, or probabilities, where you might be a gambler or a magician. Okay, so let's do a simple example of a probability. Let's say that your friend is David Copperfield, the magician, and he gives you a coin. Well, first David washes his hands, right? And then he gives you a coin. So you get a magician's coin. And you might be wondering what about this coin, aside from whether it's clean or not. You might be wondering whether or not it's a fair coin, whether it really is a 50-50 coin. The probability of heads is 0.5, and the probability of tails is 0.5. The coin is fair. Now, granted, as we saw in that Vsauce video, in real life, coins are not perfectly fair. But let's assume that in an ideal world, most coins are fair. And we're wondering if this magician's coin is biased some way. So what is the parameter of interest here? The parameter of interest is little p, which is the probability that this magician's coin comes up heads on a flip. So it's a probability. It's a success probability. Let's say that a head is a success. But on the other hand, there's the complementary probability, Q. Q is the failure probability. Q is 1 minus P. It's the complement. It's the probability that this coin comes up tails on a flip. So we have a binomial experiment here involving this magician's coin, where a success is a head and a failure is a tail. Q and P are complementary probabilities. They add up to 1. So is the coin fair? Is it 0.5 for P, 0.5 for Q? Is it biased? Is it 0.8 for P and 0.2 for Q, or maybe vice versa? Well, let's estimate these probabilities. And to estimate these probabilities, we're going to use a sample proportion. Because you can also think of these probabilities as proportions. In principle, imagine a coin being flipped infinitely many times. What proportion of the flips will come up heads? For a fair coin, it should be about 1/2 by the law of large numbers. So we can often frame problems as either probability questions or proportion questions. Okay, so the sample proportion, p hat, is obtained by x over n, where x is the number of successes, the number of heads we get when we flip the coin. Okay, and n is the number of trials, the number of flips. The number of flips or trials. So for example, let's say that you take David's coin and you flip it 100 times. You take David's magician's coin and you flip the coin 100 times. So n, the number of trials, you could say the sample size, is 100 flips. And let's say that we actually see 60 heads. We flip the coin 100 times and we see 60 heads. A head is a success. That's the thing we're counting. X equals 60 heads. Well, then what would be the sample proportion of heads in our sample when we flip the coin 100 times? Well, p hat here, the sample proportion of heads would be x over n. 60 heads over 100 flips. Or 0.6, or 60%. Which makes sense. If we flip the coin a bunch of times and 60% of the flips turned up heads, it makes sense that we take as our sample proportion 60%, or 0.6. So what is the sample proportion of tails? Again, we can think of p hat up here. We can think of p hat as the sample success probability or proportion. We can think of q here as the sample failure probability or proportion. And how do we get q hat? Q hat is 1 minus p hat. It's the complement. So the complement here would be 1 minus the 0.6 or 0.4. So if the sample success probability, p hat, is 0.6, then the sample failure probability, q hat, is going to be 0.4. So based on our sample, it's a 60-40 coin. We got 60% heads, 40% tails in our 100 flips. So overall, based on our sample data, these are our best point estimates for p and q. P hat is 0.6, q hat is 0.4. And again, these are our best estimates for p and q, which is the true success probability and failure probability in a way from the overall population, if you imagine the coin being flipped infinitely many times. So let's say that capital X is the number of heads that we get when we flip this coin n times. In this case, n was 100. Now, before we actually flip the coin, X is a random variable. I'll write that out. Okay, down here. Before we flip the coin, X is a random variable. We don't know yet what value we're going to get for sure, because we can't predict the future. However, although we can't predict the future, we can find, in principle, a probability distribution for X if we knew what P was, right? So before we flip the coin, X is a random variable. We don't know its value yet, but we do know that X has a probability distribution. And before, in lesson 23, we knew what that distribution was because we knew we had a binomial distribution, right? This is a binomial experiment when we're flipping coins and counting heads. We have a fixed number of trials, say 100 flips. And before, in lesson 23, we assumed that we knew that the coin was fair or that the probability of heads was, say, 0.6. But here's the problem now. Now, the problem is that we don't know what P is. See, back in lesson 23, I basically let you assume that P was 0.5 in the event of a fair coin, or that P was 0.6 or 0.7 or whatever. But the problem now is that we don't know what P is. So in fact, here's the idea. See, before, we knew what P was. In lesson 23, before, we knew what P was, okay? And then we would describe the distribution for X. We would describe, I'll do this. We would describe the distribution of X. So we get some handle on what we think X could be. What could be the number of heads we actually get. But now we're going to do something different. Now we're going to flip the coin a bunch of times, right? We're going to flip the coin a bunch of times, and we're going to get values for X, the number of heads, and also the corresponding statistic, P hat, okay, which is the sample probability of heads, successes. Okay, P hat was this guy over here. And from this information, from actually flipping the coin and getting sample results from all of this, we're going to try to estimate P. So we're kind of going in reverse. Before, we assumed we knew what P was. For a fair coin, P is 0.5. And then we would basically try to describe what's going to happen in our sample. What will be the number of heads that we get? We can describe the distribution as a binomial distribution. But now we're going to do the reverse. We're going to start by actually flipping the coin, getting a value for X, the number of heads, and also P hat, the sample proportion or probability of heads. And from this information, we're going to try to infer and estimate the true value for P, the true probability of heads. This is inference. Before, it was straight up probability, but now this is inference. We're trying to infer something about the actual parameter of interest, P. Okay, so we want to know what this is. We're trying to estimate P. That's our ultimate goal here. We're trying to estimate P. P hat here is our point estimate. P hat here is our point estimate for P, as we've mentioned before. And Q hat is our point estimate for Q, the failure probability. Okay, but now in this lesson, we're going to also talk about an interval estimate for P, a confidence interval. Okay, now remember that when we consider the number of heads, it has a binomial distribution. Before we flip the coin, X has a binomial distribution. So what about the methods we're going to use in this lesson? Well, we're going to rely on the normal approximation to the binomial distribution. Because remember, the binomial distribution, it involved that wacky formula, right? And it was kind of hard to manage. You potentially had all these probabilities to add up. But with a normal approximation, we're able to make the analysis a lot cleaner. Now, under what conditions could we apply the normal approximation? If NP was at least 5, and if NQ was at least 5. Okay, but wait a minute. We don't know what P and Q are yet. So instead, we're going to use P hat instead of P, the sample proportion or probability instead of P, and Q hat, the sample failure probability or proportion instead of Q. So to verify that we can use the normal approximation, we're going to show that NP hat is at least 5 and NQ hat is at least 5. It turns out, as I'll discuss later on, NP hat is just the number of successes, the number of heads, and Q hat is the number of failures, the number of tails. So it's easy to count. So for example, if we get these sample results here, if we get 60 heads and 100 flips, then NP hat right off the bat will be 60 based on our sample results. And the number of tails would be 40, 60 heads and 40 tails. Notice that both of these are way above 5. They're both way above 5, which means that a normal approximation will be very appropriate. And we are not going to apply continuity corrections. You can be thankful for that. No continuity corrections. Although in principle, they can make things better. Okay, next up, we're going to get to business. What formulas do we use to find confidence intervals for P? Next time.